All right, folks, so here we're looking at three different ramps, all starting from the same height, but with different shapes. And if we scooch over to the side here, we can get an idea for how those shapes differ. So we've got one out in front that's just a straight line down, one that curves, so it's really steep at the beginning and not steep flatter, it's flatter at the bottom. And then the other one is flatter at the top and then really steep at the bottom. So we're going to try and answer two questions here about this. First, if we drop a ball on each ramp at the same time, which one's going to win the race? Which one gets to the bottom first? And then the second question, which actually we probably should answer first, is which ball is going to get to the bottom of its ramp with the greatest speed? So not which one gets there earliest, but whenever it gets to the bottom, which one will have the greatest speed? And how do we know? So for each of these different ramp shapes, we're going to think through changes in energy and associated changes in speed. So to start with, the straight ramp outlined in red here, if we thought about kinetic energy on that one and how that changes, or sorry, potential energy over time and how that changes. So we'll make a little graph here. Potential energy, and this will be the X position. I measured this out. This is, we'll call that 0. And this is it's 1.2 meters away. So we'll put our 0 here and 1.2 meters over there. Okay, and then let's see. We'll talk through then what is changing with regard to potential energy. We'll look at kinetic energy and we'll look at speed. So potential energy depends on height. And on this one, we start out with our maximum height at the very beginning when x is 0. And we end up at 1.2 meters, we have a height of 0. We have no more height anymore, so we're down to 0 potential energy. And then all the way through, height is changing at a consistent rate. It's a straight line, so it's a consistent change. So then we would expect to see a straight line for the graph as well. So we'll just freehand a straight line here. Oops. There we go. Straight line decrease in potential energy because height is decreasing at a consistent rate as well. Then we'll think along the lines of kinetic energy. Well, kinetic energy depends on speed, and we don't have numbers given for speed at any point here, so we're going to have to find a different route to understand kinetic energy. I do know that when I release it up at the top of the ramp, it's going to be at a speed of 0, and it's going to get faster and faster as it rolls downhill. So I expect kinetic energy then to start at 0. I can go ahead and mark that. And to get faster and faster, since it's getting faster and faster, we've got kinetic energy increasing as it goes downhill also. The other thing we ought to keep in mind here is that important rule about total energy, which says that total energy is going to remain constant unless we have something from outside messing with our system. And the balls are just rolling down the hill. There's nothing from outside messing with the system that we're going to notice in any significant way anyway. So the total energy needs to stay the same. Now, potential energy is decreasing. If total energy is going to stay the same, kinetic energy must increase to balance out that decrease in potential. So when we lose a little potential, we have to gain a little kinetic. If we lose a lot of potential, we have to gain a lot of kinetic. The graph on the left shows that we're steadily losing potential energy all the way down to 0. So here on the kinetic energy graph, we must end up with all that starting potential energy turning into kinetic energy by the very end. We start at 0, we end at the same value that we started at back over here. And straight line on both these graphs. We're steadily losing potential energy, steadily gaining kinetic energy. Last thing we're going to do then is think along the lines of speed. 0, and we'll have our 1.2 meters here. Now, speed and kinetic energy are related. There's actually a square in there. It's speed squared in the kinetic energy equation. We are going to ignore that right now. That changes the shape a little bit, but won't actually impact our overall predictions here. And most of us don't have the math background at this point to include the effect of that square there. So instead, we're just going to say whenever kinetic energy increases, that must mean that speed increased as well. So if we started out at 0 kinetic energy, we have to start at 0 speed. If we end at a maximum kinetic energy, we have to end at a maximum speed. And we'll just make the shape the same in between. It's not really the same, but we'll forget about that until you've had a little more math background. Not this year, by the by. That'll be future science classes. Okay, so there's our work for the straight graph. Steady decrease in potential energy, steady increase in kinetic energy and speed. Didn't mean to do that. Okay. Next up, let's look at the curvy graph here, or one of the curvy ramps. So we're going to start with potential energy, and then we got 1.2 meters out here. Now this one's a little different. This one has a big steep drop at the beginning, so we lose a lot of height right at the beginning, but then it almost levels out at the bottom, so we have a big area at the end where we're not really changing height. So we start out at our highest point, maximum potential energy. We're going to end at a height of 0, so 0 potential energy. We're going to have a big drop of potential energy at the beginning and a little drop at the end. So that means we're going to start with a steep graph, but have it kind of leveling out over time. Now onto our kinetic energy graph. 0 and all the way to 1.2 meters. We start out at rest, so no kinetic energy. By the end of the ramp, it's lost all of its potential energy, so all of that's become kinetic energy, so up here to our maximum level. And then looking at the general shape, we had a big drop in potential energy at the beginning. It doesn't just go away, it turns into kinetic energy. So if we have a big drop in one, we have to have a big increase in the other. Big drop in potential energy at the beginning, little drop at the end. So we have to have a big increase in kinetic energy at the beginning, big increase, and then a little increase at the end. So it starts steep and gets flatter. And then last up, our speed graph, which is going to look have the same shape as our kinetic energy. So again, we start out at a speed of 0. We're going to get to our maximum speed, and it's going to be a big change at the beginning, a little change at the end. There we go. Last one, starting with the potential energy. Potential energy here is 0 to 1.2 meters in the x direction. All right, on this one, we have a pretty flat section at the beginning, so not much change in height, which also means not much change in potential energy. It does still start at a maximum, and it still ends at 0, but we have a small change at the beginning and a big change at the end. So it's pretty flat at the beginning, and then a big change toward the end. So the shapes of these potential energy graphs are very close to the shapes of the ramps themselves. Next up, kinetic energy. We've got, let's see, from 0 to 1.2 meters. And we start at rest, so no kinetic energy. By the end, all the potential energy is gone. It's all turned into kinetic energy again. We have almost no change at the beginning and a big change at the end for potential energy. So we want to have that same shape or that same trend represented here. So very little change at the beginning and then a bigger and bigger change as we get to the end. So it gets steeper over time. And then last one, our speed graph should look like our kinetic energy graph. Speed and kinetic energy very closely tied. Start at a speed of 0 and at our maximum speed. So I wrote a V, we'll have it there, speed. And I guess I was doing it on the blue one too. Oh well. And then we have a slow change at the beginning and a rapid change at the end. Now, as far as which one is going to get to the bottom with the fastest speed, well, if we say that one of them is going to get to the bottom with a faster speed than any of the others, since speed is tied to kinetic energy, we could also say then that that one would have more kinetic energy than the others when it got to the bottom. Now, where does that kinetic energy come from? It didn't used to be kinetic energy, it used to be potential energy. So if we have one that gets down to the bottom at a faster speed than the others, it must have had more kinetic energy when it got there than the others, which means it must have started with more potential energy than the others. Now, how does something have more potential energy? How does one ball have more potential energy than the other? Well, it could have more mass, but they all have the same mass. It could have a larger value for gravity, but they're all here on the Earth, so it's 9.8 meters per second squared for all of them. The only other option would be that it has a higher height at the beginning, but if we look into the pictures here, we see that they all start at the same height. So we don't have a mechanism to have one starting at a higher height than the others, which means, tracing back the other direction, all three balls are going to start at the same height. So all three balls will start with the same potential energy. For all three balls, that potential energy all turns into kinetic energy. So for all three balls, they end with the same kinetic energy. And if kinetic energy at the end is the same for all three, then the speed must also be the same at the end for all three. Now, as far as which one wins the race, well, let's check out the video for that and see. Okay, so time to test this out here. I'm going to drop all three balls at once. And if you can't tell from the video perspective, you've got the red ball on the flat, the straight ramp. The white and red striped one is on the ramp that curves down, so it's really steep at the beginning and flat at the bottom. And then the purple one is on the one that's flat up the top and it curves down afterward. And I'm kind of messed up on the ramps here so that they can't actually start at exactly the same position, but it turns out it's not that close. It doesn't actually make much of a difference here. So here we go. On your mark, get set, go! All right, so a pretty clear winner here. The ramp that slopes downward early on is going to be the one that wins the race. Second place goes to the straight ramp. Last place, we have this one that's flat up at the top. They all end at the same speed because they all start with the same potential energy and they all lose it all, and so that all turns into kinetic energy. But it's a question of when does that change take place. And so on this one, we see that it stays up high for a lot of that race, which means it keeps a lot of potential energy, not much kinetic energy. So this whole time it's going really slow. It's not until it gets down here that it starts picking up significant amounts of speed. The straight ramp, that one is gathering speed, losing potential energy at a consistent rate, gathering kinetic energy, and gathering speed at a consistent rate, all the way down. But this one, we have this really sudden drop at the beginning, so it loses a lot of potential energy by, say, the halfway mark, which means it's gained a lot of kinetic energy, which means it's gotten a lot faster early on in the race, and then stays fast through the rest of the race. So this one spends the majority of its time at that faster speed, meaning that this is the one that wins the race.